Okay, in this video, we're going to talk about a very important theorem, Taylor's theorem, which is going to be a way for us to find the power series for certain functions. We talked about in the previous video that if you have a function you'd like a power series for, and it happens to fit the form for the sum of a geometric series, like 1 over 1 minus x, where you can think of this as the first term over 1 minus r. Your first term would be 1, your r value is x, and you just multiply each term by x, and you get a nice power series for 1 over 1 minus x. And we saw some things you can do with that, right? You can find 1 over 1 plus x. Using a similar technique, you can integrate that to find the series for ln of 1 plus x. So that has some use to it. But what if we want a function to find a power series for a function that doesn't resemble a geometric series formula for the sum? Can we still find a power series? And the answer is yes, using Taylor's formula. And so Taylor's formula tells us how you can find a power series for any function, including this one if we wanted to. It's an infinite series, so you can condense this in sigma notation, and it would be the summation from 0 to infinity, the nth derivative evaluated at your center, we'll talk about that, times x minus c to the n over n factorial. If you expand this out term for term, starting with 0, you just get f of c. N is 1 is the first derivative of c times x minus c to the first, and of course 1 factorial is 1. When n is 2, you get f double prime of c, x minus c squared over 2 factorial, and so forth. So there'll be times when you're going to want just the first few terms, like my first example here. Find the first 4 non-zero terms of the power series for f of x equals 1 over x squared, centered at 2. So we want c to be 2 in this case. Because it says the first 4 non-zero terms, we're going to use the expanded form and take it out. Now 4 terms, unless one of these is 0, is actually going to take us out to the third derivative, x minus c cubed over 3 factorial. So sometimes, like if we go this far, another way to express this is you're going to have a polynomial that's degree 3. So we could also have said a degree 3 power series or polynomial. Okay, so just plugging right in, c has a value of 2. We're going to get f of 2 plus f prime of 2 times x minus 2, f double prime of 2, x minus 2 squared over 2 factorial, and then my third term. And all that's left to do now is to just fill in the value of my function and the derivatives, all my derivatives at 2. So I take a bunch of derivatives. That's what we have down here. A bunch of derivatives of that. I'm going to plug in 2. It's a lot of algebra and simplifying, and you get a bunch of fractions. And if you put those back in for f of 2, f prime of 2, f double prime of 2, and so forth, you get a polynomial. I believe I simplify the polynomial back. Yeah. So that polynomial reduced gives you 1/4 minus 1/4 x minus 2 plus 3/16 times x minus 2 squared minus 1/8 times x minus 2 cubed. So it's a cubic polynomial that represents that function. Now, suppose we wanted not just the first 4 terms, but we wanted the entire series. Then we're going to use the condensed sigma notation, because that captures all infinite terms. Now, one challenge we're going to have is the nth derivative evaluated at 2. We have to find a formula that will help us predict what any derivative of our function is at 2. Okay? And then x minus 2 to the n over n factorial, that's just going to automatically go there. So off to the side here, this is kind of our challenge here. To find a formula for our nth derivative at 2, we just start taking derivatives, which we did on the previous page, but now we're looking for a pattern. And one of the tricks we'll see to finding a pattern is don't simplify this, otherwise you're going to miss out on the pattern. So first derivative, negative 2x to the negative 3. When I bring the negative 3 down, I'm not going to make that 6. I'm going to leave it as negative 3 times negative 2, x to the negative 4. Next derivative, don't multiply it out, just leave it expanded. And we start to see a pattern, right? Each of those negatives can be thought of as a negative 1. So we have 3 powers of negative 1. And then 4 times 3 times 2, it's only missing a 1, but it's the same thing. That's 4 factorial. And then I could write that as over x to the 5th. My fourth derivative, if I brought the negative 5 down, now I would have 1, 2, 3, 4 negative 1s, 5 factorial over x to the 6th. And then to write it in terms of n, you can tell based on the evidence we have here that on my nth derivative, I would have negative 1 to the n. Notice on the power of my derivative, I have to do one more factorial. So it's n plus 1 factorial. And then it's divided by x. Notice that my power of x in the bottom is 2 more every single time than the derivative I was on. When n was 3, that's 5. When n is 4, that's 6. So in general, it will be x to the n plus 2. Final step is you want your derivative evaluated at 2. So I'm just going to end up plugging 2 in for x. And there's my formula for the nth derivative evaluated at 2. Put it right back in here. Make a little room for it. And now we have, that is the power series for 1 over x squared. Now, of course, we were talking about on the previous video, we were talking about power series. Once you find a power series for a function, you may want to know its interval of convergence. So I'll just remind you, you can still use the ratio test and work out an interval of convergence. This one happens to converge between 0 and 4. Okay, if you run through a ratio test. Okay, that's probably good practice to make sure you can do that. Okay. Now, some series are either easier than others to find a power series for. E to the x is probably the easiest example. Oh yeah, terminology. We call these power series, Taylor series is another name for them. If someone asks for a Maclaurin series, Maclaurin and Taylor were both mathematicians who studied infinite series. Taylor got credit for the infinite series centered anywhere at some number. Maclaurin, when someone asks for a Maclaurin series, it's understood that the center is 0. Okay, so I don't have to say that. On the next time, if I say find a Maclaurin series, I don't have to tell you that. You just need to know that the center is 0 when it's Maclaurin. So it's just a special case of Taylor's formula. So my C is 0, nth derivative evaluated at 0, x minus 0 to the n over n factorial. Similarly, as the last one, I have to find a pattern for my nth derivative evaluated at 0, but this one's a piece of cake, right? Every derivative is e to the x. So if I plug in 0, I'm going to get e to the 0, which is 1. So that just turns into 1 every single time, and I get my series for e to the x. There it is in sigma notation, expanded out. Looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Now you should probably be able to do this. I think we may have done it on a previous video, but if you did a radius of convergence, you would find that this thing converges everywhere from negative infinity to positive infinity, which is not surprising because you have a factorial in the denominator. It's going to make those terms small really fast. Okay, the next one I'd like to do is the series for sine of x. And it's a little, I want the whole thing ultimately, but let's try to find the first 3 non-zero terms first, and you'll see why. So the center is 0, it's a Maclaurin series. So I'm going to need f of 0 plus f prime of 0 times x, f double prime of 0, x squared over 2 factorial, and then the third derivative, and so forth. Now, one thing about sine of x is right off the bat, f of 0 is 0. So that first term, which should have been f of 0, it's actually 0, and that doesn't count. It said we wanted the first three non-zero terms. First derivative is cosine, that evaluated at 0 is 1. Back to sine, negative sine, you're going to get 0 again. Next derivative is negative cosine, gives you negative 1. And then notice when you get to your fourth derivative, you're back to sine of x, which is back here. And every time, you're just going to keep running through the same four derivatives every time, every fourth power, every multiple of 4. So when you put that all in, here's what we end up with. Sine of x would be the first term was 0, 1x, 0, negative 1x cubed over 3 factorial, and then 0, x to the 5th, or 5 factorial, and so forth. So my first three non-zero terms would end up right there. But if you kept going, it's pretty clear this entire series is just going to involve the odd powers, right? X minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so forth, which can be expressed in sigma notation. To make your power skip by 2, you're going to need a 2n. And then I had to add 1 to that because I'm starting at 0, and I want my first power to be 1. Okay. And again, you should probably be able to do this. Make sure you can use a ratio test. But again, since I have a factorial in the bottom, it's going to converge for all values of x. This is going to generate very small fractions. Now, here's what's cool. We get to use something we learned earlier. Let's say I want to find the power series for cosine of x now, since I just did one for sine. On a previous video, we saw that if you already know the series for sine of x, and we know the derivative of sine of x is cosine of x, then I can just take the derivative of both sides to get a power series for cosine of x. Now this derivative, if you bring that down, you get 3 over 3 factorial, 5 over 5 factorial, 7 over 7 factorial. But remember how those work. 3 factorial is really 3 times 2 factorial. So the 3's would cancel, and that would just really be 2 factorial. Same thing for 5 factorial, right? That's 5 times 4 factorial. The 5's would cancel. And so the series for cosine is kind of similar to sine, except it involves the even powers. And it's alternating with factorials. And there's the sigma notation. Now we also know by the series differentiation theorem we discussed earlier that because the radius of convergence, because sine of x converged between negative infinity and positive infinity, cosine will too, you're guaranteed. So this converges everywhere. Okay. All right. Now we've seen using Taylor's theorem to find a power series from our first example can be pretty tedious. But remember, once you've found a power series for a particular function, we can often manipulate it to find series for other functions. For example, I just took the derivative of sine to get the series for cosine. Say I wanted to find a Maclaurin series for f of x equals x times e to the x cubed. If I try to use Taylor's theorem, Taylor's formula, remember what you have to do is take a bunch of derivatives of that function. That's going to get really ugly because you're going to need a product rule, right off the bat. And then each derivative after that's going to get worse. But here's how you can manipulate a series that we know. E to the x, we have that series right here. So if I wanted e to the x cubed, I can just imagine plugging in x cubed for all of those x's. And I get this. And you can even do that in here in the sigma notation. If I replace that x with x cubed, that's going to become x to the 3n. Now I want to multiply by x to get my function. So if I multiply both sides by x, and you can do that in sigma notation, you have a series now for x times e to the x cubed. Written out, it would look like this. In sigma notation, if you just combine, that's x to the 3n plus 1 over n factorial. another way you can find power series for functions is by multiplying them. Here I want to find the first three terms of the power series, the Maclaurin series, for sine of x times cosine of x. Here's your series for sine of x. Here's your series for cosine of x. And I'm going to multiply them. Now, it seems a little strange because these are infinite polynomials, right? But remember, I only need the first three terms. So I don't have to multiply this all the way out. So what I would do is just start. X times 1 is x. X times that is negative x cubed over 2 factorial. X to the 5th over 4 factorial, dot, dot, dot. Now move on. Negative x cubed over 3 factorial times 1 would go right there. That's going to give you x to the 5th positive over 3 factorial, 2 factorial, and so forth. And then if I go to the x to the 5th over 5 factorial, just times 1 is right there. Now, can you see that if I were to move on, if I keep going, I'm going to end up with higher powers of x. I'm never going to get anything lower than x to the 5th anymore if I kept going either with the x to the 5th or if I moved on to my next term. And since I only need the first three terms, I can then just combine these. So I have x. Remember, 2 factorial is really 2. 3 factorial is 6. If you find a common denominator, negative 1/2 minus 1/6 is negative 2/3 x cubed. And all I did here, if you worked out the numbers, work these out as numbers and add those fractions with those denominators, you should get 2/15 x to the 5th. And so that's the first three terms of the power series for sine of x times cosine of x. Now, you can also, there's a kind of a clever way, a sneaky way, you could have found that same first three terms, and that's with using a trig identity. Remember, the double angle identity for sine of 2x is 2 sine x cosine of x, and we were looking for a series for sine x times cosine x. So if you divide that by 2, then to find this series, we can manipulate the power series for sine of x. The first three terms are there. If I put in 2x for each of those x's, I get this. And then if I take half of that, multiply each term by a half, look what happens. I get the exact same first three terms that we had on the previous page. And so there we go, right here. You distribute that 1/2, that's the same series we had. So my final note there, that's why knowing trig identities are good, right? It's good to know some because they can help you out. Okay, next video we'll do some more we'll derive some more Taylor polynomials for some trickier functions, including the square root function. That one's a little bit tough, so